Hello, everyone. Thank you for joining us. Today, we will host the webinar, How to Gain More Insight with Dual EDS Detectors. Today, we will have two presenters. The first is Sheng Mu. He joined us joined EDX in 2018 as one of our applications engineer. And then he will be followed by Jens Raffelson, who joined EDX in 2014 as an applications manager. They will go ahead and start talking and carry on from there. If you have any questions in the meantime, please go ahead and submit them to the questions pane. At the end of the presentation, they will go ahead and answer any questions that came in and go from there. Go ahead.
Thank you, Jennifer, for the introduction. Good morning, good afternoon, good evening, everyone. Welcome to today's webinar on dual detectors. Starting with an outline of this talk, first of all, I'll introduce the dual detector setup and geometry. Then I will move on to benefits of dual detectors, such as throughput gain, resolution, mitigation of topographic and shadowing artifacts, followed by dual detector feature in Apex software. After this, I will hand it over to Jens. Jens will go through a bunch of mapping and spectra examples to show the applications of dual detectors and to wrap up this talk. This is the pole piece of SEM. Around the pole piece, we have secondary electron detector, EDS, and WDS detectors. For dual EDS detector setup, the two SDD detectors are positioned at different azimuth angles and collect data simultaneously. The two sets of data are stored separately and they can be combined. This is the side view of a dual detector system. For each detector, the elevation angle is the angle between the horizontal and the detector normal. And the intersection distance is the distance in millimeters between the pole piece to where the electron beam intersects the detector normal. These two parameters are set when the system is installed and won't change when you move the sample around. Working distance is the distance from the pole piece to the sample surface. And the takeoff angle is the angle between the X-ray trajectory and the sample surface. These two parameters do change when you move the sample. If a flat sample is placed at the intersection, for each detector, the takeoff angle equals the elevation angle, and the intersection distance is equal to the working distance. In general terms, the final number of usable X-rays analyzed by a given EDS system depends on the number of X-rays generated in the sample, the fraction of the generated X-rays that reaches the detector chip, the detector chip response, and the efficiency of the electronics processing the signal. The input count per second seen by a given EDS detector is highly dependent on the sample, electron acceleration voltage used, and the beam current at the sample. Keeping these parameters the same, the number that is considered to have the biggest impact on the input counts per second is detector chip area. Although detection area is an easy and intuitive number to understand, we have to be careful when trying to estimate the number of detected X-rays based on detection area, because the solid angle of the detector can vary significantly depending on which microscope or microscope port the detector is mounted on, and how far the detector can be inserted. When using the same conditions, a dual detector system actually doubles the detection area and consequently doubles the throughput while maintaining single detector's resolution. Some background information on throughput versus resolution. The chart on the left shows the pulse of one X-ray. The rise time equals the fall time, and we call it amp time. You may also hear pulse processing time from other vendors. The rise time or amp time sets the absolute limit for the number of counts a given SDD can handle without overlapping electron clouds. The chart in the middle shows output counts per second versus input counts per second at different amp times. The black curve in the very bottom is the slowest amp time at 7.68 microseconds, while the yellow curve represents the fastest amp time at 0.12 microseconds. You can see shorter amp times give higher throughput, but shorter amp times mean worse resolution. The chart on the right shows detector resolution as a function of amp time for different detectors. Black and green curves are previous generation detectors with 30 and 70 millimeter square chip sizes. Red and blue are current generation detectors with the same sizes. The trend is resolution decreases as the amp time becomes shorter. For previous generation detectors, the degradation is greater. Current generation detectors are equipped with CMOS-based preamps, which allow further reductions in capacitance and noise, providing better performance and high count rates and better low energy response. So at the shortest amp time, the resolution are still below 150 eV. However, the previous generation detectors are around 200 eV at this amp time. Here are two options to double the throughput. You may use a faster amp time, but the drawback is it gives you worse resolution. However, a dual detector system doubles the throughput while keep single detector's resolution. This brings us many benefits. For a fixed amount of time, statistics are doubled, resulting in higher quality data. For example, for mapping, the statistics at single pixel level are doubled. This is extremely useful for processing net intensity or quant maps, since these map types require better statistics. For quantitative analysis, the peak-to-background quant model also requires better statistics to obtain good results. By using dual detectors, alternatively, you can reduce the collection time by 50% to get the same quality data, which means a more efficient data collection. For those samples that cannot tolerate high beam currents, dual detectors enable better quality data to be obtained through use of lower beam currents. A comparison between dual detectors and a larger area detector. Sometimes people may wonder if I should get a dual detector system or a single detector with larger chip size. Compared to a larger area detector with 2 times chip size and with the same electronics, dual detectors have higher sound output count rate. because each detector receives less input counts than the larger area detector to ensure more efficient conversion. In addition, larger area detectors has worse resolution at fast M times due to base resolution and increasing tailing. I'm using this animation to illustrate charge collection and why we will see tailing when the detector size is large. This is the cross-section of a detector chip. When X-rays hit the entrance window on the bottom, electron hole pairs are generated at position 1, 2, 3. The electrons will be driven by the drift field to the anode on the top, where the charge is being collected. The electrons generated closer to the perimeter will take longer time to reach the anode, as indicated by the drift time in the chart below. Cloud 1 is generated very close to the anode in the chip center, so its drift time is the shortest. Cloud 3 is the closest one to the perimeter, so it takes the longest time, and the drift time of Cloud 2 is in between 1 and 3. The greater the distance between the point where X-ray is absorbed and the anode, the more the electron cloud spreads out. At fast M times, the pulse may not reach its full peak height. This means not all electrons are collected, resulting in tailing on the low energy side of peaks. This picture is an overlay of manganese peaks using different M times. Black is the slowest M time, which gives the best resolution. Blue is the fastest M time. It shows tailing on the left-hand side of the manganese K alpha peak. Tailing decreases resolution. For larger area detectors running at fast M times, since the radius of the chip is greater, on average, the electron clouds will travel longer distance. In addition, processing times is shorter. Tailing becomes severer. For a dual detector system, each detector receives less counts, so dual detectors have room to run at a slower M time to get better resolution without sacrificing throughput. To summarize, the dual detectors have higher throughput with better resolution than larger area detectors. When analyzing non-ideal samples, dual detectors work better than a single detector. This is a tilted sample. It's facing towards the detector on the right, but tilting away from the detector on the left. On the left-hand side, the takeoff angle is small, which means the escape path for X-rays is longer. X-rays will travel a longer distance to reach the detector, and the low-energy X-rays are subject to more absorption by the sample matrix. As a result, the low-energy peaks in the spectrum will be lower. On the right-hand side, the large takeoff angle gives a shorter escape path for X-rays. Low-energy X-rays are subject to less absorption, resulting in higher low-energy peaks in spectrum. For particles, they are subject to the same effect when the electron beam is positioned at different portions of a particle. The takeoff angles can be smaller or larger than normal. When dual detectors are used, the effects associated with takeoff angle variations will be reduced by merging the two sets of data. For particles or other small objects adjacent to large objects, the large objects may create a shadow zone for the smaller objects. Here, particle A is much larger than particle B. When analyzing particle B, X-rays excited from particle B won't have a path to detector 1. The count rate will be very low in particle B. If detector 2 is mounted on the other side, particle B is not shadowed anymore, and the count rate will go back to normal. Same thing applies to a sample with a rough surface. The X-ray path from the analyzing area to detect 1 will be blocked by the surface topography, but it has a path to detector 2 on the other side. Actually, this kind of topographic effect also happens on sample surfaces that you think they are flat. Data shows significant differences can be seen between sample polished with 1 micron diamond and 0.1 micron alumina polish. Signals are attenuated more or less, and dual detector will help in this case. Moving on to software feature. Dual detector feature is available in Apex 2.1 version. For those of you who don't know, Apex 2.1 is EDX's latest version of software for integrated EDS and EBSD applications. This user-friendly 64-bit software ensures high quality, accurate results, and increased productivity with its easy-to-use interface, lifetime graphic display, and simultaneous data collection and review capability. For dual detector feature, supported detectors are Octane Elect and Octane Elite. By default, the 2 detectors will run at the same amp time. Each detector has individual detector cooling control and slide control if it has a motorized slide. From the drop-down menu on ribbon bar, you can select data from either detector or display them together. You also have the option to merge the 2 sets of data. More detail on next slide. For spectra collection, there are multiple display options. Quant numbers from dual detectors can be displayed together. By selecting detector signals from the ribbon bar, you can display spectrum from either detector or overlay spectra from the 2 detectors. In the spectrum window on the left, the red solid spectrum is from 1 detector, and the outline spectrum is from the other detector. By clicking on the merge button on the ribbon bar, you can merge the spectra. The spectrum displayed on the right is a merged spectrum from 2 detectors. The quant confidence is increased by averaging quant numbers from both detectors. For mapping, you can display map data from either detector or merged map data. If you have used our software, you may notice selection of rebuilt maps has been moved from project tree to ribbon bar to give a cleaner project tree view. For single detector or merged data, you can choose from the ribbon bar to display rebuilt ROI, net intensity, or quant maps. Okay, at this point, I'm handing it over to Jens to go through some dual detector data.
Thank you, Shang. So with that, we're going to take a look at what does all of this actually mean and what do you gain from having a dual detector system. There's a few different applications we're going to go through, and I'm going to start with the increased statistics, as Shang mentioned. So the sample I use for this is it's a floor tile, which gives pretty pictures. We see here in the insert, that's the backscatter image of the sample. And the other benefit, besides just pretty pictures, is that there's a bunch of stuff going on in the sample, basically. It's a ceramic, so we have our primary elements being oxide and silicon. But then we have a bunch of other things in there. There's some iron inclusions and calcium inclusions, aluminum. There's some salt in there, sodium and chlorine, probably mostly from dirty fingers, as we've been using this sample for a while. And we also have a phosphorus and zirconium overlap, which makes this one pretty interesting. That is the small peak you see just on the right-hand side of the silicon peak. Just to give you an overview of the sample, here we have a few images. Top left, we have the backscatter image. And then center, we have the counts per second image. So this is just a sum total of all X-rays per pixel. So this is basically an image of the X-ray yield. It's very good for highlighting topography differences, as we'll see a little later, but also just gives you a good overview of where we get X-rays from in the sample. Top right, we have the oxygen map. It's a rock, so yes, pretty much everything has oxygen in it. Bottom left, we have our silicon map. We can see there's 3 distinct phases here, or 4 if we count the ones where there's no too little silicon. And if we correlate the oxygen silicon map, we can see the bright part in the bottom left is probably a quartz. Then we have the calcium map in the center bottom, where we can see we have a band of calcium running through the center of the sample and some inclusions. And then bottom right, we have the iron map, where we can see the calcium correlates with the iron, but we also have some other iron inclusions in the right-hand side. But for what we're doing here, I am concentrating on the phosphorus and zirconium. And top here, we have the phosphorus maps. Top left is from Detector 1, center is from Detector 2, and right is the merged maps, where we basically go through every single pixel and add the spectrum from that pixel for both maps together to create a third map. Excuse me. And in the bottom, we do the same thing for the zircon. So looking at these, one thing to note is that these are region of interest maps. So these are pure raw counts, which means we do not compensate for any peak overlaps. So if you compare the phosphorus and the zircon, you can see they are very similar. Some of the grains in there have different intensities, but we have the same grain showing up in both maps. And we look at the merged, it's hard to tell because we scaled everything back to the same contrast, but there's little difference to see there. However, if we go in and use these to do a rebuild, in this case a weight percent, I'm going to toggle back and forth a few times here, we can see that things change. We get the zircon and the phosphorus separated, so we pull out the different particles, and now we can see which ones are actually zircon and which ones are actually phosphorus. And depending on your screen resolution and everything, you can see some differences in the merged weight percent map. It looks kind of subtle, but we have some of the grains where we have a bit of noise are cleared up in the weight percent merged map, because we now have the sum statistics of the 2 individual maps. When we do the deconvolution and background subtraction, it often just comes down to how many counts do we have, what's our statistics in there, and merging them really helps bring that up. Since it's subtle, I have gone in and blown the contrast and brightness up completely, and that's what we're showing here. So now we can really see the difference. This is, for practical purposes, we would mostly be interested in separating the grains. But what I'm doing here is blowing it up so we can really see the stuff that's outside the grains. And we can see in detector 1 and detector 2 for the phosphorus, that quartz phase we have down in the bottom right gives a pretty significant contribution to the two maps. So that's the increased background most likely that we can't separate out because we don't have enough statistics to do it. But when we sum these two together, sum the spectra together, and then do the math on the summed map, we now have sufficient statistics to do a much better job of the background subtraction. Now we can see we get a much more uniform background below our particles of interest. The same thing for the zircon map we have down the bottom. We can see there is a slight contribution from the silicon, but not too much. We have more of a contribution from the iron inclusions. And when we then add the two together, add the spectra together, not the maps, the spectra, and do math on it, we can get rid of most of that iron, the strong iron inclusion and the silicon contribution. We can now see there's a bit of residual from the calcium iron that we could pull out by increasing the statistics, again, counting for longer simply. But this shows that you can take advantage of the dual detector setup and basically increase your statistics and get better, more accurate results out of it, do a better job of the modeling and the subtraction. Of course, when it comes to statistics, dual detector is great. You could count twice as long with the same detector and get the same result. So this is not something that you cannot do with a single detector, or you can count with a larger detector as well. This is not unique to a dual detector setup. It can be done with a single detector, but of course at the cost of time. The next part, however, when we get into topography, is much more difficult with a single detector versus a dual detector. Here I've taken a sample with a bunch of pretty large quartz crystals in there. So obviously this is not a flat sample in any way, shape, or form. And I have the counts per second maps shown here from detector 1 on the left and detector 2 on the right. Again, the dark areas in a counts per second map is where you get low X-ray counts or no X-ray counts. And in this case, that would be caused by detector shadowing, that your X-rays are generated, but they have to pass through parts of the sample, so they never make it out to the detector. If we look at detector 1, you can see the surfaces that are facing towards the top of the image upright. So detector 1 is looking from the top of the screen down towards the sample, whereas the opposite is true from detector 2. So these are opposite of each other. One is looking up and one is looking down. So now we have two maps, and both of them show artifacts, topography artifacts in there. There's a couple of tricks we can do. What I did before was merging the maps, so adding the spectra together on a pixel by pixel basis. For topography, that's not necessarily the way to go. If we look at this feature here in the detector 1, the left-hand side one, you can see that's dark because it's facing away from the detector, whereas for detector 2, the right-hand side one, it's bright. But when I add those two values together, I get something that's in between, the dull gray we're showing on the far right in the merged or summed map here. So we're not really doing anything to get rid of topography just by merging or summing the maps. Instead, we get an increase in statistics in the areas both detectors can see, but we also get shadows from both detectors. So depending on what you're looking for, this is actually making your data worse. For the flat sample we had before, summing or merging the spectra was a great idea because you're increasing the statistics. And we don't have any shadowing because it's a flat sample, but here it gives us other problems. Another trick that can be done, though, is taking a max of each of the images. So here, instead of going in and adding the counts from each pixel to generate a third map, we go in and look at, for each pixel, which map has the highest count. And we use that set of counts to create the third map. And now we can see the region we had before, where we ended up with a dull gray, we now have a lot more signal, or not more signal, but uniform signal. And we can compensate for the topography to a large extent. We get a much more true image of the sample. Of course, we still have problems in the regions where we get no data at all, where we are completely shadowed on both detectors. But this does help us give a reduction in the topography part of the signal. It should be noted that we're only using the signal from one detector or the other. So we're not increasing statistics or getting better spectra from doing this. This is purely for the imaging part of it. However, it still carries benefits for more analytical purposes. So here I grabbed an iron oxide, piece of rusted junk in not so scientific terms. And rust tends to be very rough on the surface, as we can see in these two images. So we have a lot of topography and shadow zones in these two images. And I mapped it out and built the phosphorus map based on this, where phosphorus is one of the contaminants that can be cause for various failures and rust in some samples like this. If we look at the two maps, we can see here in the left-hand side, the detector 1, the counts per second shows nice signal. And if we look at the corresponding phosphorus map in the bottom left, we have a bunch of particles in there. We do the same thing on the detector 2. On the right-hand side, we can see I have shadow here, and consequently, I don't see any phosphorus signal down in the bottom map. Vice versa, over in this region, I have shadowing on detector 1 and don't see anything in the phosphorus map, whereas my detector 2 gives me a reasonable signal. So if we're looking for how much contaminant do we have on this sample, we could go in and we just did a very basic particle count on this, or a pixel count. And we can see detector 1, we have about 539 particles, detector 2, 512, and we calculated the particles per area as well. Now, this might not look like a big difference. There's only about 400 particles per area missing between the two. But the point is that you are missing different particles in each of them. So if we want to have a more realistic assessment of the contamination for this sample, what we would do is go in and build the max map. So here we can see in the top we have the CPS, detector 1 and detector 2, and then we look at the map, the max map. We have a lot of the topography completely compensated for. We still have a few areas where we don't get any signal on either detector, but we have a significant improvement in the image here. And the same thing holds true for the phosphorus we show down the bottom. It's a little harder to see because you don't have the same uniform signal, it's more individual particles. And now if we go in and look at how many particles are we seeing, we're now at 7,795 particles per square millimeter. So almost 1,000 particles more, or a little more than 1,000 particles more compared to which detector we were looking at when we looked at just the individual detector maps. So that is a significant difference. Looking at one detector, either detector 1 or detector 2, versus the max signal, we see about 10 to 20% increase in the number of particles we detect. So by using this max signal between the two detectors, we can reduce the topography effects, and we can get a much more accurate description of what's the contamination and what's the contamination density on this sample. And this is something that would be very difficult to do with a single detector setup. So for mapping the dual detector has advantages in that you can take good data and make it better just by adding it together. You could do the same thing for the topography. So most people hopefully would know that samples with topography are bad for quantification. It's bad in a lot of other ways. But taking two bad maps and doing math on them, either summing or doing the max spectrum, we get better data out of it, more representative data. Not necessarily something we want to do quant on, but still better data than you would have with a single detector. For the quant aspect of it, this is a little different because this is all about statistics. So here I took in Almandine Garnet, a reference sample that we have, and we have what the composition is supposed to be here. We have, obviously, it's oxidized, so we have a lot of oxygen. We have the primaries besides that being iron and silicon, aluminum, magnesium, and then we're starting to get down to the minors and trace levels with calcium and magnesium definitely being a trace. I collected spectra at different configurations here, different times, 1, 2, 5, 10, 20, and 50 seconds, and with different input count rates, 5, 10, and 100,000 input count rates. I kept the amp time the same for both detectors to make sure I don't have any resolution contributions, distorting things in there. So basically, this is an exercise in changing the statistics. How many counts do we have in the spectrum? So if we start by looking at the silicon peak here, which is supposed to be about 18% weight percent composition, and go in and plot it out, we can see here I'm a little low on silicon, and I think I have a good idea of why that is. We'll get to that a little later. But we can see here when we have low count rates, the 5 and to some extent the 20, and low acquisition times, we get lower numbers. We see a large deviation here in the beginning, and it starts to approach the numbers we see for higher count rates, the 100,000 counts that we have in green up here. So this is the weight percent we get out after averaging all the spectra. I did 10 acquisitions per point just to build up statistics a bit. And if we look at the standard deviation between those 10 spectra, we can see sort of the same thing. At low count rates, short acquisition times, you have a lot of variation in the spectra, but as you count longer, that variation drops down, standard deviation decreases, and when we go to something like 50 seconds, we are closing in on the different count rates. So all this really shows is that the longer you count, the better statistics, the better results you get. And of course, if you have two detectors, to get the same statistics, you would only need to count half as long. Where the statistics really start to matter, though, is when we start to look at trace elements. So if you look at this manganese peak, note the height of the iron relative to the oxygen and silicon signal. And now we're going to zoom in on the iron peak, and now note the height of the manganese peak relative to that iron peak. So this really is a very small peak, very low counts we have in there. And for the observant viewer, you would also notice that something's missing in my standards. The values I showed in the beginning are not quite true. If we look at this iron K beta, you can see there's a tail on the left-hand side, so I'm quite confident there's some cobalt in my sample that's not accounted for. So one of these days, I should go through and measure this out with WDS and get the true composition. But looking at the manganese here, we can see the true weight percent, 0.46, is what is shown in the dashed line in the top. And we get quite large deviations in the beginning with the 5,000 counts per second input counts. So instead of 0.46, I get values of 1.4 or 1, but we can see it tails out and approaches the true value as we increase the acquisition time. Alternatively, we can increase the count rates, and we can see it again, it tails out faster. With the 100,000 counts per second, it's very flat in the deviations. And we can see that in the bottom as well, the standard deviations of the spectra I collected, that the longer we count, or the higher rates we count at, the smaller the standard deviations of the results will be. So this all really comes down to statistics. We can count longer and get better results. And if you have a dual detector, well, you have the same size, you can do it in half the time. There's nothing here you can't do with a single detector. It's just a matter of the time it takes. So this is similar to what we did with the floor tile sample, where we have a nice flat sample and we can just add the spectra together, get better statistics, and do math on that to increase our reliability. If we do something similar to the sample with topography, we get slightly different results between mapping and spectra. So this is a lead sulfide, Galena sample, and I have quite a bit of topography on the sample, as you can see in the image here. So I started off with just a single acquisition in the flat-ish part of the sample, and we can see that it's supposed to be 13.4 weight% of sulfur, 86.6 weight% of lead. And there's a slight difference between the two detectors, but they're pretty close to the certified values. Again, there's statistics and other things that play into this, so this is not something I would be worried about, this slight discrepancy in the quant results. I chose this because, well, for one thing, I had a sample that had a relatively known composition on a lot of topography, but also to show that we have severe overlaps here. The lead and sulfur are very convoluted, so that makes it a little tricky sample from that perspective as well. If I now go in and put my spot on one of the tilted or rough parts of the surface, you can see my spectra change significantly. And if I look at the spectra from the two detectors, I can see detector 1, there's a big problem here. If you look at the high energy range, you can see I have a hump in the high energy range and it drops down in the low energy range. And that is not normal behavior if you have a flat sample. Obviously, this is not a flat sample, but what's going on here is that you have additional absorption. So high energy X-rays can escape through more material quite easily, whereas the low energy X-rays will be attenuated. So we have a lot of attenuation going on here. And if I look at the low energy range, we can see our main sulfur lead peaks are heavily attenuated and we get a lot of carbon and oxygen. So what is happening here is that we hit the sample and we generate X-rays right where we're hitting. But some of these will be going through the epoxy we have outside the sample, and some of it will be going through the lead sample, the Galena sample itself. The stuff that's going through the epoxy and some of the other things that go through can fluoresce the carbon and oxygen in the epoxy that's embedded in. And that's what we see here in the low energy range, that we have very high carbon and oxygen peaks that we did not see before in the flat part of the sample. So here we really have a problem with the absorption taking place outside where we're hitting the sample and secondary fluorescence. And if you look at the quant numbers, they are very, very bad. We have 5.7 sulfur and 26.3 lead compared to the 13.4 and 86.6. The other detector is looking from the bottom up, and that one doesn't have as much additional things going on. There is a bit more fluorescence. We see some increase in carbon oxygen, but we get more reasonable results here. We're relatively close to the known composition of the sample. But if we take the spectra and add them together, things start to go south. You're taking bad data and adding not great, but acceptable data on top of it, and that decreases the quality. If I go to a second spot here, now we are in a region where we have shadow from the top and fluorescence in the carbon from the bottom detector. And we can see now both detectors are giving us pretty bad results, and obviously when we add the bad results together, we get bad results. So whereas for mapping, we can use the two detectors to get rid of the topography to some extent, we can't do the same for spectra. So for the spectra, we have basically the matrix is if you have good data from detector 1 and good data from detector 2 and add it together, we get better data. We're increasing our statistics. But you can't compensate for bad data by adding good data on top of it. If you take good data and bad data and add it together, you still get bad data. And if you take bad data and bad data, you get very bad data. So the dual detector for spectrum and quant is mostly a tool to increase your statistics. For major elements, it might not matter too much. You can get those in a relatively short amount of time and get good results, as we saw with the silicon. But if you're doing trace element analysis, having the increased statistics or collection efficiency really can get you better results in a much shorter amount of time and give you more confidence in your results. So, to the summary, if we have the same conditions, the dual detectors will double the throughput and maintain single detector resolution, so you can get higher map quality or faster data collection. If you have a beam-sensitive sample, you are inherently or typically limited in how much current you can put down. So you can't just crank up the current to get better statistics with a single detector, but here dual detectors will give you the ability to have better data quality in the same amount of time as a single detector with lower beam currents. In general, if you have a detector of twice the size, dual detectors will have higher throughput and better resolution because we can run each individual detector slower and still maintain the same output count. And for the quant analysis, you want to be careful about what you're doing with a dual detector. We always save the spectrum from each detector, and you would manually have to select, yes, I want to merge this data in the software. We do that because if you have bad data on one detector, you can ruin your analysis by just merging them. You have to be careful about what you're doing if your sample is not ideal. If it is ideal, by all means, add them together and you reap the benefits of additional statistics. Alternatively, you can look at the average of the quant results, so not average the spectra, but average the quant results, and in that way build more confidence. For the mapping part of it, the dual detector is quite efficient at showing the topography for one, but also you can mitigate the topography and shadow artifacts by doing various tricks, such as the max map you can build from the two detectors. And with that, let's jump over to the questions. There's one that we frequently get, whether the presentation will be available online. Yes, it will. It will take some time to build it up and have it uploaded, but we generally make them available through our web portal or web page. Let me just forgot to skip over to that one. That's the last page we have here, where we have our web address and webinars are on the website. You can find them in there. There is a setup that you have to go through and sign up for it, but it is available on demand, including all the ones we've done in the past. So there's a lot of good information in there as well. Question of hardware limitations for dual detector configurations. Yes, there is. First of all, your microscope should be able to fit two detectors. Some of the smaller microscopes, you will only have space to add one EDS detector on there. Even some of the bigger ones, depending on how much other stuff you have mounted. But it's primarily which ports are available on the microscope. There are some microscopes where that can give us a bit of additional complications if the ports are not at the same angle. if one is at 35 degrees and the other is at 30 or something like that. For mapping, it doesn't really matter as long as you don't do quantitative maps or really want the quantitative results out of it. You can still do the topography mitigation and things like that. But for quant analysis, you want to be careful about merging the spectra. We save the geometry with each detector, so each detector will have the correct results. But adding the spectra together and doing quant on that becomes a little tricky because now you have two different geometry configurations. So the merged spectrum becomes kind of an unknown. But in general, as long as there's a port to mount the detector on, we can put it on there. There's some other things to consider, but in general, bigger microscope chambers can easily accommodate two detectors. There's the questions of two detectors. Are the detectors both the same size? In the example I showed, yes. It doesn't necessarily have to be. You can have different detector sizes on the different detectors. I would generally recommend trying to keep them the same, simply because count scale with size. So if you have a small area detector and a large area detector, obviously the small area will see a lot less counts than the large area. So you don't get the double the benefit. It will be a different scaling in that regard. And you can end up with a few more complications with, if one detector sees more counts, it will also see more sum peaks and things like that. But it is possible to have two detectors with different sizes. Topography and single detector. I said that we can do, for the spectrum acquisition, you can just acquire for a longer period of time, and that will give you the same results as having two detectors. In principle, you can do the same tricks as I did with the topography on in the maps with a single detector setup, but it's a lot more complicated. So the idea is that I look at the sample from two different directions. So what I miss in one direction, I'll see in the other direction. In principle, you can rotate your sample and acquire a second map with your single detector setup. But now you will have to realign the maps. So basically rotate them back and find the same features in both maps and correlate them before you can just add them together or do a max function on it. So yes, it is possible to do the same thing as I'm doing with the dual detector here with a single detector, but it is a lot more work, and you have to go to various third-party software. You have to be very careful about your states alignment and things like that to get the same results as I do with basically the click of a button. We have one more question here. A dual detector with EBSD. So yes, we can acquire two spectra at the same time in an EBSD configuration, but chances are you don't want to do that. If you're doing EBSD, typically your sample will be tilted at 70 degrees, and on most microscopes, that would mean that you're tilted towards one EDS detector and away from the other. So in most configurations, basically your second detector will show you the signal from the backside of the stage, which is 0. There are some microscopes where we can mount two detectors on the same side with the axis or the stage tilting towards both detectors. So in that case, you would get the dual spectra and double the counts. However, for most applications with EBSD, dual detector is not too beneficial, simply because in EBSD, often you're at high voltage and relatively high currents to run it relatively fast, which means you have, in most cases, a boatload of EDS counts. You're not statistics limited most of the time with EBSD. If you are doing things on sensitive samples or trying to do low voltage, low beam current EBSD, yes, then you would have a benefit of dual detectors. But again, your microscope would need to be able to accommodate for that with the available ports. And having 2 EDS detectors or 2 ports available in the tilt direction of the sample is not a common configuration. Okay, with that, I think we're through most of the questions. I would like to say thank you for attending, and I think Jen has a few words as we wrap up. Thank you.
Thank you, Jens, and definitely thank you, Shang Chang. Both of you did a wonderful presentation. For anybody on the phone, as well as thank you for attending. If you have any questions or want more information about dual EDS detectors, please visit any of these additional resources. And if you have any questions that come up after the webinar, feel free to contact us at info.edax@amatech.com, and we can definitely answer any of these questions offline. We appreciate you joining us today, and we shall talk to you later. Thank you.